Hey, IB Physics kids, Mr. Tima here. Going to talk to you about two-dimensional waves, wave fronts. We're going to talk about water for the most part. I'm going to be jumping around back and forth on a couple screens here, so hopefully you don't get seasick. And here we go. No pun intended. All right. So first of all, we need to understand this idea of what a wave front is. Okay, what a wave front is. Okay, so one way to look at this real quick is if we look at this PhET simulation, we can see that a wave front is kind of like the distance of kind of between these little wave particles. So this is like, imagine a little oil can dropping in there, or if you want to think about water just dropping in, okay, something like that. Okay, kind of goes in there. We can just do a simple little pulse. There's one, there's two. So we can figure out the period, the frequency, everything from that. All right. If you just want to look at a regular old wave front panel, like a wave generator, like a wave pool at like Zoombezi Bay, these are wave fronts. We call these planar wave fronts, if you will. If we have a barrier, okay, if we have a one slit barrier, you'll see that this is actually something called diffraction, which we're going to get to. And there's going to be a part in the notes that's going to talk about diffraction of a double slit and stuff like that with intensity. So you'll see all this and everything like this. What's cool is these are water waves. The same thing happens with sound or with a laser light. It doesn't matter. A laser generator is going to follow the same path. Okay, a sound wave generator is going to follow the same path. It's going to do the same thing. So what's really kind of crazy is that it doesn't matter if you're talking about water, sound, or laser light. They all follow the same pattern. All right. Oh, got to get going there. There we go. Okay, so a wave front. All right, there are raised circular wave fronts and planar wave fronts, which I talked about. So a plane wave front would be that flat one like we talked about, like an ocean wave as it hits a shore. Okay, a circular wave front would be like that drop that came out. It moves out in all directions. All right, and a parallel or plane wave front, we talk about those rays. Rays on a circular emanate out from a circle. Rays on a planar wave front only move one direction. So we got that going. Little picture for you, shows you the distance, what the wavelength on a circular wavefront would be. There's your wavefront, there's your ray. This is how you would kind of make your sine curve off of those. Reflection, as we've talked about, it doesn't matter if it's sound. It doesn't matter if it's all of that stuff. It doesn't matter. Planar sound or whatever. It's all going to follow the same principles, okay, of how that reflection off of that. So you got to kind of think three-dimensionally there. The laws of reflection, you should have learned about this in physical science, but basically the angle of incidence is equal to the angle of reflection, which means if this thing comes in at an angle of 40 degrees, it's going to leave at an angle of 40 degrees. Okay, these angles are equal to each other. A little picture for you. That's an old school one. That's actually from my science textbook back when I was in school, but it kind of makes sense there for you. Okay. And I should just say without skipping over there are PhET simulations. That's what I was using earlier, and you're welcome to go try any of these on your own time if you want. All right, so a change in medium. When a wave passes from one medium to another, its velocity changes. For example, when a water wave passes from deep water to shallow water, it slows down. You may have experienced this as you run into water. Like if you ever run into the ocean or into a pool from shallow, when that happens, you actually slow down. The lower half of your body slows down and you actually fall. You tend to fall into the water. You bend, you fall into the medium. Okay, so for example, like this light wave, when it hits, it's going to bend into the medium. It kind of bends downward or into the medium. If this was you running into the water, you tend to fall into the water, your face, because the top part of your body moves faster than your lower part of your body. And here's just another look at that. Okay. The speed of the wave as it enters is the same at all points, and the angle that it bends in is equal at all points. It just may take longer to get to that spot for it to do that. This is why a pencil looks bent in water, because the light waves are bending into the medium. So we have this equation, which is Snell's law, which is very important. All right, and you'll see this pop back up again in some upcoming notes. But basically, this is the angle of incidence. Okay, so you do the sine of the angle of incidence The angle of refraction would be the sine of the angle of refraction is equal to the velocity coming in and the velocity in that refracted part. It's a ratio. So you're going to have basically three of these parts, and you'll have to solve for the unknown part. And remember, since it's angles, we're talking about degrees. The last in circular motion, we were in radians. And here we're going to be back to degrees, because anytime you're messing with degrees, you need to be in degree mode. So again, here's a little practice problem. Okay, so it says the water is the velocity of the water, okay, out here, okay, has a velocity of 20 meters per second. It enters a shallow region where its velocity is now here. So we can think of this as like V1, and we can think of this guy as V2. It really doesn't matter which one's which, you just need to be consistent. If the angle of incidence of the water to the shallow region is 50 degrees, what is the angle of refraction? So if we look at this, here's our equation, right? This is your V1. This is your V2. You have the sine of this angle, okay? Oh, did it get a little cut off there? But basically, if you do that, you're going to find that to be 20 over 15 is your velocities, right? So your velocity is 1.33, and then you solve for the sine of r, and it got a little cut off there, but it's 0.576. Okay, sorry, got a little cut off there. So our answer is actually, and then you got to take the inverse sine, and you get an answer of 35 point. I don't know why that's all jacked up on there. 35.2 degrees would be the angle. So it goes from 50 degrees to 35.2 degrees angle of incident. Right, diffraction, which I showed you on the other page, is it bends around there. As the slit or as the opening, we call it a slit, but as that slit or opening gets closer, we get a more rounded wave front. Okay, because it's like this middle part kind of doesn't get bent because it's got enough room to get through. All right. There's some actual water waves that I took with a camera. Okay, but you can see that on that sim that we just did. It also bends around an object the opposite way. What if it's not a slip? What if it's going around here? So a lot of fishermen do this. Fishermen back in history knew that fish like to congregate. Fish would tend to sit behind rocks and kind of close in there, because if you think about it, if you're a little fishy, you can sit if the river's going like this, right? A fish can sit back here. It doesn't have to swim as hard because the current's going around and it kind of bends around. But back here, it's pretty dead water, as they say. They don't have to swim as hard. So on smaller rocks, the fish will tend to congregate closer to the middle of those rocks, so that way they don't have to swim as hard. Okay, if you've ever been on a river or something, or been whitewater rafting, you follow the raft, sometimes when you go around a rock and you're out of the boat, it'll kind of suck you. You feel like it sucks you in here. Well, you're just being pulled kind of to that dead water area. All right, again, with interference, remember, if crest and a trough and a trough line up, you're going to have constructive and it's going to grow. If they are not lined up, they will phase or be out of phase and cancel each other out. Again, another diagram just to show you that right there. Again, they really want you to understand this point in these chapters. All right, let's watch a little video clip from Dr. Quantum. Some really cool stuff here. All righty, sorry about that. There's our simulation going. Here we go. Give me 1 second.
What they taught us in school isn't really the way it is, and that our senses are playing tricks on us. You just gotta wonder, what is this reality that we find ourselves in? Quantum physics says it's all just waves of information. Do I believe that? I hope so. Yikes! And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. It was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
So, what's crazy about that is the idea that we as observers can collapse the wave function. The idea that just by observing something can send an interference pattern to which will cause something to change what it is doing. This is why it is so hard for us to see exactly what like a electron is doing. And that's the quantum stuff. And we'll talk a little bit more about that when we get to that section in the book. All right, last little thing, and then we'll be done for today. Two boys are playing in a swimming pool and make identical waves that travel towards each other. The boys are 10 meters apart. So here's our boys right here. These are our boys. Um, Yep, the boys are right here. Okay. All right. Each wavelength is 2 meters. Their little sister is swimming from one boy to the other. Okay. All right. When she is 4 meters away from the first boy, will she be on a big wave or a crest, if you will? Or is she going to be on a small wave, which means, or not crest, but a constructive wave? Or is she going to be on like a destructive wave? What do you think? Okay. Is she going to be on a big wave or is she going to be on a small wave? Take a second and take a guess. Well, the solution is she's going to be in phase. They will add, so she will be on a big wave. Okay, well, how do we do that? Well, we assume if we have here, we have it's 4 meters, right? So we need to get two waves in here. Well, there's one. I know it's a horrible drawing, but there's two. Okay, and 6 here, so we need to get three. There's 1, 2, and 3. If you notice, those waves are going to be in phase with each other because they would be, this isn't, 2 meters is our wavelength. Since we know our wavelength's 2 meters, we know that the tops of those waves would be there, and boom, we're going up. All right, that person's going to be going up. That girl's going to be going up. If she was 5 meters, if for some reason she was over here, she'd be on a really small wave. They'd still be in phase with each other, but she'd be at the small wave part. Okay, so it all has to do with that. All right, you're going to have some practice problems here. Pretty standard. Hopefully, if you have questions, make sure you're reaching out. Mr. Tima, out.